An Olympic athlete throws a javelin at 6 different angles above the horizontal, each with the same speed. Here are the different angles. Which 2 throws cause the javelin to land the same distance away? What we need to do is derive an equation that relates range, or horizontal distance, to the launch angle. So I'm going to make some room here. All right, let's get a pen. Okay, so if we have a projectile taking off with v naught, we know that the x, so here's our angle, the x component is going to be related to the cosine of the angle. So that's going to be the hypotenuse times cosine theta. Because we have our right triangle, we know that cosine theta is adjacent over hypotenuse, and adjacent is v naught x, and hypotenuse is v naught. So therefore v naught x equals v naught times cosine theta. We also know then that the y component, I'm going to erase this, the y component is related to sine of the angle. So it's the hypotenuse times sine theta. Okay, so now let's go start with our second kinematics equation in the x and the y dimension. So we have x equals x naught plus v naught t plus 1/2 at squared. But in the x dimension, we're going to assume in the launch that we're starting at a point of 0, 0. Therefore, x initial becomes 0. And in the x dimension, there's no acceleration. So that's also 0. So therefore, in the x dimension, the range, where we land horizontally, is going to be equal to v naught t. So what's actually important to us is the launch speed in the x dimension, and also how long the projectile's in the air. We need to know the air time. Now, we can turn v naught into v naught cosine theta, because this is actually v naught just in the x dimension. So we're going to make that x equals v naught times cosine theta times t. So instead of just having v naught x, we can make that v naught cosine theta. That way we're going to be able to relate this equation with the y dimension. Okay, in the y dimension, make this smaller, we have y naught plus v naught in the y dimension times t plus 1/2 at squared. Because we're starting at 0, 0, y naught goes away. All right, and v naught y is v naught times sine theta. So I'm going to go ahead and replace that now. Times t, and we know that a is negative g, because it's an object in free fall near Earth's surface. So this is going to become negative g over 2 times t squared. Oh, I forgot one other thing. The final position, so when it lands, so at that x location we're interested in, the y value is 0, right? Because it's landed. It's at the same vertical height that it started at. So I'm actually going to also erase this y and make that 0. Okay. So now we can actually go ahead and solve this for t. So I'm going to move this piece to the other side. So add it to both sides. Okay, I'm going to cancel out 1t from both sides. And then I'm going to rearrange. So I'm going to multiply both sides by 2 over g to get rid of it from the left side. And we get t equals 2 v naught sine t over g. Okay, so that's the air time. Now we're going to combine it with this equation in order to relate it to range. So I'm going to do that over here. So we have x equals, all right, v naught times cosine theta times t, which is here. So we're going to plug that in for t. We get 2 v naught sine theta over g. Okay, so now let's simplify. We have v naught and another v naught. So that's going to become v naught squared. We also have 2 sine theta cosine theta, which if you remember from math class, that's the double angle theorem. 2 sine theta cosine theta is equal to sine 2 theta. and we still have that all over g. So we want to know, here's the piece of the equation that's going to relate the angle with the distance. These things are not going to play a role here. This is all that we're changing is theta. So when is sine 2 theta going to be the same? Well, you might remember from the unit circle that complementary angles, if you double them, they become supplementary angles, which add up to 180, right? So let's start with 20 and 70. These are complementary angles. They add up to 90, which means if you double both of them, they add up to 180. Now, if you have angles that add up to 180, so for example, you have an angle here, and then you have 70, or I guess that would be 40, so we're doubling it, right? So this is our 40-degree angle here. And then we have like a 140-degree angle to here. And those add up to 180, right? So they add up to over here. They have the same y component, right? They're both at the same y value, which means they have the same sine value. Therefore, if you plug 20 in here, it would be sine of 40. Sine of 40 is equal to sine of 140. The answer is the complementary angles. They're going to have the same values for sine 2 theta. So they're going to give you the same horizontal range. The answer is B.